What a wonderful winter world it is. Better stay inside and build a robot. Hey, there are my glasses. Let's get started. Welcome back to Element 14 Presents. I'm Clem, and in 2 previous episodes we have built this FPV rover robot and the arm for it. And people on the Element 14 community asked for, can you make a robot with legs that works like that? And the answer is probably. Let's try it out. My previous robots were directly driven by a Raspberry Pi. We used a web interface to control them, and that was perfectly fine because they were driven over the network via commands, so it's basically like driving a rover on a different planet somewhere. Feels exactly like a Mars rover. But for a legged robot, there is an aspect in between. Those legs have to be coordinated, and if they don't move like they should, the robot doesn't walk anywhere, it just stumbles around and doesn't go really. So we need real-time computations for that. So a microcontroller in between the Raspberry Pi and the leg mechanics. So of course I looked up how to build a legged robot, and the conclusion is they basically all come to the same system. 6 legs is the easiest one because 3 legs are stable at any point, so you would have the easiest gait. And quadrupeds, so like 4-legged robots, are very popular because they need dynamic walking, and that just looks awesome. How do they make them walk? Well, with like a ton of math. Math. So if you have watched like my previous videos, you may notice that I don't like big calculations and trigonometry and stuff. I like to find easy solutions that I also understand. And for like walking patterns, I thought, do you really need to make all those calculations just to make some basic movements? Because when we drive our robot over the network, like the rover before, we will just give the commands like go forward, go left, go right, something like that. So it should coordinate on its own. Does it really need all that math? Let's see how little math we can use to make that robot walk. Since I made my first project, a lot of things have changed. There are new Raspberry Pis like the Compute Module 4 or the 02, and I thought, hey, I want my board that I have to make for this project compatible with all the Raspberry Pis. So no matter which one you want to use for the top level controls or for like AI functions or video streaming or object recognition, you can use whatever you want, and it just plugs into the board and the microcontroller on there does the coordination for the legs. That's the idea. We need some custom hardware for that, so off to my computer to KiCad and let's design some custom hardware. Welcome to my computer and to KiCad. There's a lot of stuff going on this one sheet of KiCad. I've made it in one sheet because I need to like see things at a glance to figure them out. So that is very dense, but we only focus on the main things. So here, this big thing and that big thing are the CM4, the compute modules, interfacing pins, the 100 pin connectors. We have a USB-C. This is for voltage spike protections, ESD safety. Then we have 2 driver chips for our servos. These are called LED here because originally those are LED driver circuits, but they are perfect for servos. We have 2 of those, and here's the first thing that I encountered later. So you should be aware of that. This addressing is perfectly fine. Pull them out down via a 10K resistor to ground. But this is not, because that results in an illegal address, so we can't access that chip. For our purposes, these would give us 32 channels of servos, quite a lot, but we actually only need 14? No, we need 12 of those. So we use just 12 of the first bank of servos. That's enough for this project, but that is the reason why I just won't publish that schematic without any changes. There are some stuff that we need to sort out first before this could get into production. We have an ESP32S2 here, which is the CPU that we use to control all these servos. We have the GPIOs here. If you want to use a normal Raspberry Pi, you plug it in here, and it basically accesses the same pins like the GPIOs, like the CM4. But the CM4 also has this camera connector here, so you can directly access the camera from the CM4, and if you would use a normal Raspberry Pi, you would use the connector on the Pi itself. Over here we got some power distribution. Basically this is compatible with RC batteries, so you put in like a 2-cell LiPo and it gets converted down to 5 volts. We have 2 of these LM1085 in parallel, so we can supply enough current, and we also have an independent power source for the 3.3 volt logic for the LED drivers and for the microcontroller. Yeah, that is the schematic. Let's look at the board layout. There's quite some layout going on here. You can see this gets quite complicated. This is a 4-layer board. So now we can see all the layers. There's a lot of stuff going on, but you can see here is the power distribution, here is the connector for the camera, and I have specifically routed those traces to be at the same lengths. That's why they wiggle around here. So the signals get to where they belong at the same time. This is not very critical with this camera connector. It's more critical with HDMI outputs, and it's really critical if you do RAM and stuff. But I should always match the trace lengths. If we look at that in 3D, then this is how it looks. We have multiple buttons here. These two are for the CM4, and these two are for the microcontroller. So this is the flash button. If you hold that down while resetting, it puts the microcontroller into download mode, where it can flash new programs onto it. And that's like a dedicated reset for it. And here we have a dedicated reset and a freely usable button for the CM4. As you can guess, we use GPIO2 and make that the button to shut down and to boot up the system when we want to. Yeah, and we have one of these driver circuits on each side, so they have not so long distances to cover, so we can route all these traces without much interference, and also kinda match them in length. And then there's like a line going through here for I2C, and we have a UART connection over here that makes the Raspberry Pi talk to the microcontroller. So all these two talk with each other is over UART, and they tell the other one, go here, go there, do that command, make that action, or give feedback about the status. And basically that is like the direct evolving thing of the board we made last time with the FPV rover project. Welcome to the Arduino code for this project. As always, first we have to declare some libraries that we want to use. The servos that I use are a bit atypical to normal standard servos. They are 9-gram servos with metal gears, but they also have an analog output that we don't use on this project, but that would give us like a closed loop that we could use to more precisely control our servos and to use that as an input, which we may do on a future episode. We have a speed divider here that is used in a smooth servo driving segment of the code to make sure we know how fast the servos are going. then we have basically our kinematic model in there, as I said, as little math as possible. This is our function to make the servos move and to make them move smooth. Then we have the move to position function, which basically says we set new values, a new pose, if you will. And when you call move to position, then it will just execute that. And that is also a for loop. It iterates over all these joints and puts the new value that we have entered in new pose to that servo. So now we have our first like real animation sequence. This is the stand up command. This is moving forward. This took like ages to figure out. It's pretty complicated. Then we have move right, which is not turning right in that sense. It's basically making a step right. And then we have left, which is exactly opposite. It basically makes a step right. And then we have another function that's reset position. That is basically go into your standard position if you may have lost track of where you are. Do a standard position, a T-pose, and then stand up again and do your thing again. And to demonstrate this, we basically have made a little sequence. It stands up, then walks a little bit forward, goes a little bit left, walks forward again, goes right, and resets its position. And that's it. And if you now make like a serial interface that accepts command from the Pi, then you basically can issue these commands and it will execute it. The Pi doesn't have to drive the servos, is not occupied with coordinating the movements. That's all in the microcontroller. And basically your high-level programming can focus on the important stuff. It's pretty much like you operate. You don't have to think about breathing or how to move your fingers and stuff. You just do it because you said move finger somewhere. Do you do that? Anyway, let's build this thing. I couldn't even get enough servos for a 6-legged robot, so we're doing a quadruped. And when I got my servos, I realized, hey, those are the really fancy ones that have like a potentiometer output, so you can verify the position they are in. So like really good robotic servos actually. And I didn't took advantage of that in my hardware design. So that goes on the list for a future project. Leave it in the comments below if you want to see like a closed loop robot system thingy. To physically build my robot, I use PLA, PETG, my own engineering resin, a wild mix of stuff. I use multiple machines at once to get it faster and use the cheaper materials first to get the right shapes and then print it in the better materials for the final assembly. And because things change around, I have to print them over and over again until all the parts fit. I had to 3D print a lot of iterations of my design because I made a critical error. I did not really think about how the servos are orientated and how you would move them in code. And like having different servo orientations around the robot makes everything a lot more complicated. So first I tried to build it like really nice, symmetrical, and then in the code it was like a mess. But I have included that code that didn't work out, it just was too complicated to address all the stuff, on element14.com in the downloads folder. So I reprinted everything and gave all the servos the same basic orientation, so it's a lot easier to address where they need to go. Like this. Hip, and do this and do that. Yeah. Constructing it in the easy way is also helpful for the code. Looks like we have a little robot here. We have code, we have a battery, we have some hardware, we have a lot of cables. Let's see if this thing can stand up and walk. In this episode we have built a robotic walking robot base for our FPV rover. If you combine what we did today with the FPV rover project that we did previously on this show and also the robot arm, you get the legged version of a Wi-Fi controlled robot that you can control over the network like a rover on a different planet. So this project is in its infancy and we have to iron out some kinks, and I want to have your ideas and your input. What should we do next? Focus on smoother walking and making that more reliable, teaching it some tricks maybe? Or is it the automation with including the compute module or another Raspberry Pi and the camera to make it like AI-driven targeting specific tasks, like image recognition and following stuff? What do you think? Let us know in the Element 14 community. I gotta go. There's another project waiting for me.